The mean value theorem for definite integrals. Mean value, we already have a mean value theorem just in general, which tells us something about an average slope. Um, it seems reasonable that within this section where we're talking about average values of a function that we might actually have a mean value theorem. And this is the one we have, mean value theorem for definite integrals. Here it goes. If f is a continuous function on the interval from a to b, then there exists a c, also on the interval from a to b, such that f of c equals the average value of the function on that interval. Another way to say that, i.e., that f of c equals 1 over b minus a times this integral, which can also be written, just multiply both sides by that denominator, and you got f of c times b minus a. There's really only one conclusion, right? It's either this one or this one or this one, and different books write it different ways. So, we want to prove this theorem. And let me first of all point out before I prove it that there's a continuity issue here, and you definitely need f to be continuous. Because if you looked at a function that looked like this, right, let's say open there and close there, on this interval from here to there, right? If you look at the integral of that function, you'd be calculating the area under here and over here, and then you divide by the length, you'd get this height right here, so that this piece up above is the same as that piece down below. Anyway, the average value of this function might not ever be the same as the function values. You got a bunch of function values down low here, you got a bunch of function values up high there, and they never hit the average. However, if the function is continuous, then there has to be a spot where when you calculate that average value, the function will cross through it. Okay. So let's do a quick proof of that. And the way I'm going to prove it is I'm going to prove it by using the mean value theorem. So let's define another function here. Let g of x be the integral from a to x of f of t dt. All right, I'm told that f is a continuous function. G is now just the area underneath this function f from a to some variable right-hand endpoint, which I'm calling x. Okay. We note that g is differentiable because I know that g prime of x is f of x, and that's the fundamental theorem of calculus part 1. And if it's differentiable, then it's got to be continuous. So here I've got this continuous function, differentiable function on the interval from a to b, which means that the mean value theorem applies. Mean value theorem back from chapter 5 applies. Actually, I guess it's well the way back to chapter 4, wasn't it? That was Calc 1. The mean value theorem says that there exists a point C, there exists C on the interval from A to B, so that G prime of C is equal to what? The average slope. So G of B minus G of A all over B minus A. Well, G prime of C, we happen to know from up here that this is just equal to F of C. And then plugging stuff in over here, this is equal to G of B. Here's the definition of G right there. So I've got the integral from A to B of f of t dt minus g of a, that would be integral from a to a of f of t dt. Well, that's easy enough to do because the integral from a to a is going to be 0. And that's all over b minus a. So what I have here is I have that f of c is equal to the integral from a to b of f of t dt times 1 over b minus a. And so sure enough, I've got a point where the function value is equal to the average value of the function. This is the mean value theorem for definite integrals. It's essentially the mean value theorem applied to an antiderivative. There you go.